Thank you, everyone, for listening to us today. At Montevideo Labs, we work with top US tech companies, helping them to build smart data products with a quality focus always in mind. Today, we will talk about how we'd like to think about production ready software when it comes to building such products. Notebooks, they're a really good tool for creating truly reproducible research and has drastically changed the way data scientists and engineers collaborate, share ideas, and create POCs. However, if your company or product is large enough or complex enough, chances are notebooks are not enough. And we've seen many cases in which a notebook trains a model and deploys it straight to production. At that point, the notebook becomes a software artifact and is subject to all the illities we know from software engineering. Right? Do we have testability by doing that? Can we ensure maintainability, availability, all the illities? If you want to tweak the data pipeline that creates a model, can we guarantee integration is smooth? We'll show that through a demo, which we hope you find useful. Even though our example is very simplistic, it's always easy to reason about these concepts with a concrete example at hand. Finally, we'll share some takeaways from this process. Building smart data products takes collaboration between data scientists and data engineers or engineers. However, a success story for data scientists and engineers can typically mean different things. Oftentimes, some of these objectives are at conflict. And for example, it's hard to perform quick iteration for a production A/B test if we need to ensure that models being served are truly thread safe. They don't have memory leaks, they don't cause garbage collection issues, etc. At the same time, chances are that those models that better perform in terms of accuracy may require a large memory footprint and are prone to creating other performance problems, typically latency. We strongly believe that culture plays a very important role. Great products can only be built with true collaboration spirit in mind. So many times you're tempted to have data engineers and data scientists do their own thing independently. For example, let's consider the case we mentioned about deploying a model straight to production from a notebook. Even though this is common practice in many companies, it does come with some risks. We need to make sure that the assumptions that hold the training time are stable and continue to be true in the future. Typically, models need to be refreshed, and in many cases, to be successful at that, we need automated pipelines. When we inject a model as a live black box, we break part of the CI/CD chain, and if dependencies are not explicit, integratable, testable before release time, things can go wrong, unfortunately. So the advantage of integration tests is lost, and the investment made by dev organizations on continuous integration, testing, and development is undermined. In the past, we've faced a number of issues with very good models that don't play well when it's part of a UI. For example, a sales prediction model, which shows a drop in sales when expanding to a greater region, might be accurate based on the machine learning data, the testing data, but it might be incorrect or at least unintuitive to the user. Adding a unit test, for example, that checks for isotonic behavior might help catch this issue and also prevent regressions. Working independently is easy when it comes to assigning blame. The prediction is off, the system's too slow. However, this way, we're not really working together towards a common goal. We don't collaborate to explore the right trade-offs between conflicting aspects I mentioned before. So a fluid dialogue and collaborative culture here helps. Engineers, they know the very essence of how the data that lies in our data lake was constructed. It can help data scientists avoid common pitfalls in the interpretation of this data. Likewise, data scientists typically by doing analysis, they find issues with the data that might shed some light on possible upstream bugs. I had a professor a long time ago that reminded us that at the beginning, bridges, that is physical bridges, they fell down quite frequently. It took time for robust bridges and construction methods to evolve the right way, right? Likewise, 50 years ago, software had lots of bugs and products were really not great. But the industry evolved. We learned new ways to write code, new abstractions, new processes, rights and wrongs. We simply can't expect that magically now that we incorporate data science into our software efforts, Things will be different. Let's not make the same mistakes again. In an ideal world, uh, data scientist is free to choose any library, any programming language, Julia, R, Python, MATLAB, scikit-learn, deep learning for Java, whatever. The data scientist can choose the exact library that solves the exact problem at hand. In an ideal world, engineers get models that are threat safe, that they don't have any issues with the data pipelining. They're fast to predict. They don't have garbage collections. They're stateless. These kind of things are the ideals for engineers. And Spark is a really good compromise as it provides solutions to vast arrays of data science libraries. It takes care of scale. It allows data scientists and engineers to speak the same language. Plus, it comes with many guarantees when it comes to integrating it to our software products. Um, so let's focus now on a demo. Um, we want to show how to take a notebook and break it apart into modules that allow for proper software utilities. Right? We want to show an example from a book I co-wrote with Saket Mengel. On a section of this book, um, we show a problem for which we build a notebook. And this is a recommendation problem, and we provide a solution in Apache Spark as well as AWS SageMaker. The problem consists of finding theme park attractions to recommend users based on the photos taken at each attraction. If we assume that someone taking a photo of an attraction is a proxy for interest in that attraction, um, then we can use the data to find other attractions people similar to you might be interested in. This following slide is a notebook created from that problem. The notebook massages the data a bit, runs some SQL, creates an ALS, an alternating least square model, and inspects recommendations to users. Javier, how can we break apart a notebook like this, and build proper software modules?
So as Maximo said, notebooks are a great tool for research, though they are probably not enough for large products. At Montevideo Labs, we do believe that high-quality software products should be built using proper software engineering tools, such as Git for version control or an IDE, and these are not very compatible with notebooks. In this case, we created a Scala project in IntelliJ and used Maven to add the Spark dependency to it very easily. We do prefer Scala for our production code, but the concepts that we will present in this demo should apply perfectly well to any other language of your choice, such as Python. The number one key to developing highly maintainable software is to break down your solution into smaller and more cohesive components that can be composed and reused. Each of these components should be taking care of a very specific task. We do suggest that you break up your pipelines into smaller sub-pipelines that can run independently, and then you can figure out how to synchronize their inputs and their outputs. For this system, our first high-level component is an ETL, which basically takes care of loading the system's data in a form that is useful for some of the other components. In this case, we are using Spark data frames to hold our loaded data, which we will then use for populating some of the feeds in the system. The good thing about data frames is that they are lazy, so we don't actually pay the cost of materializing the intermediate results between decoupled classes and functions. These feeds are a very simple framework that we developed, which provides a way to communicate completely decoupled components very simply, and this is done by allowing a producer to put a new update into the feed and a consumer to retrieve the latest update in the feed just by complying with an implicit contract. We will show you a handy and simple implementation of these feeds that leverages the file system for durable storage. The second component in our solution is the trainer, which uses these data feeds to train any kind of recommendation model that can be used for serving recommendations. We will show you how we train a Spark ALS model like this. The last, but obviously not least important component in our system will be dedicated to serving recommendations using previously trained models. This one can be seen as a service, which receives a user ID and returns a collection of recommended attractions for the user, and it uses an underlying model to predict these recommendations. In our case, we decided that our different components should be implemented as different Scala packages, but they could as well be different modules or different repositories. and they could even be implemented in different languages as long as they comply with the feeds contracts. We also added a common package, which contains definitions and utilities that are shared by many components. The first very important definition that we encapsulated and included in our common package is everything that has to do with the Spark session. We suggest that you do this so that you have one single place where you are configuring the session. We also included the definition of our environment configurations. Allowing these properties to be configurable differently in each environment allows us to have one single artifact for our pipeline that defines the behavior of the system, which can then be adapted to running in different contexts by providing a different set of configurations. We included one implementation of this trait that retrieves the values from environmental variables, which is very convenient for a staging or a production environment. But we also added support for programmatically forcing a configuration, which is very convenient in the case of automated testing. The other important thing that is included in our common package is the definition of our feeds framework, which of course will be shared by the different components for their inputs and their outputs. We included a very simple implementation of this feed trait, which relies on a file system for writing and reading the updates that we put into the feeds. This way, every time that a new update is put into a feed, it is serialized and written in the file system in a way that it can then be read back. The implementation can easily be extended for any kind of serialization that we can implement, but we added out-of-the-box support for Parquet and for CSV. Ideally, our implementations of the feeds should support keeping a history of all the updates that were added to it, even if we will always be reading the latest update. And this, of course, will improve the auditability of our system. In the case of the file feed, we achieved that by writing the update in a folder inside the feed root, which is named after the current timestamp at the moment of writing. This is how easily we can configure a new feed, in this case, the visits feed. Each feed is stored in a given path, and we recommend that you include some version identifier in that path to have more flexibility for introducing breaking changes in its contract without breaking active consumers until they are ready for the new version. Now, let's do a deep dive into our first component, the ETL. In this case, we have defined an ETL pipeline for two different feeds, the attractions and the visits feed, which are both transformations of raw CGEAR data. Of course, for any ETL, we must define how we are reading or extracting the raw data, as well as how we are transforming it. We recommend that you encapsulate each of those two in different independent classes, which will not only make your code much easier to read and understand, but it will also improve its extensibility and its testability, which are major things when systems get big. The driver of the ETL component is a very simple program. For now, it just delegates to the right implementation to load the visits and puts them in the visits feed. And as you can see, then does the exact same thing for the attractions. Another thing that you might notice is that we are using what we call a data frame descriptor to describe both loaded data frames before storing them. And this can be very helpful for debugging and again for editability. The fact that we are encapsulating such descriptions in a special trait is not only for the sake of reusability, but also because it allows us to leverage the strategy design patterns so as to avoid expensive operations that are not necessarily always needed. And describing a data frame can of course be a very expensive operation, while not very useful in a non-debugging context. As we said, the outputs of the different drivers are stored in the feeds so that they can be retrieved by any other independent component. In this case, these feeds will be consumed by the trainer. In our next component, the trainer, we provide one implementation of an attractions recommender trainer for Spark's alternating least squares algorithm. It should be very easy to extend this component to include other algorithms as well, such as the SageMaker version introduced in the node. In the case of Spark algorithms, training a model is very easy to implement. We receive the visits data, do a very minor preparation so as to put it in the format that the algorithm expects it, and call feeds on a previously configured else instance. We recommend that you keep any data processing that is very coupled to the algorithm inside of this same scope. And when possible, you should also consider using Spark's Etl pipelines for this. We also suggest that you keep the configuration of the algorithm in a place that is very easy to find for people which are reading your code. Another important tip that should be considered for machine learning algorithms, but also for any other kind of processing that you are doing, is that you use deterministic seeds for any kind of randoms that you are generating. And in this way, you will achieve results that are reproducible at any other point in time. The train your driver program is very simple as well. It first gets the latest update of the visits feed, which is fed to the ALS algorithm to be used as training data. Here we are also adding a data frame descriptor in case we are in debug mode. We then put the model produced by the fitting algorithm into the ALS model feed so that it can be picked up by any other component in the system. The consumer of this feed, in this case, will be the recommender service, but we could as well have included any other intermediate component that validated the model in a controlled environment before shipping it to the service. Another important thing here is that this model is obviously not a data frame, but we can still leverage the feeds framework by providing support for writing and reading these models to and from a file system. We include an implementation of the recommender that uses previously trained Spark ALS model to perform predictions. As you might know, Spark ML models require that we create a data frame and then Spark will create a prediction for each record you need. In our case, this is not very convenient as we only want to do a prediction for one single user. And creating a data frame for it is expensive in terms of computational efficiency, which affects the latency of the predictions, and it's also not very neat in terms of code. You can watch last year's Summit presentation in which Maximo and I presented an extension of Spark that we developed for supporting row-level predictions in a Spark-agnostic environment. And of course, this can be very convenient when your service has a low latency requirement. That said, we believe that this implementation is good enough for the purpose of this demo at least. Okay, so apart from that, we also included a very convenient decoration of the attractions recommender service. In this case, this decoration allows us to have different implementations of the recommender coexisting in one same service, in a way that we can deterministically decide in which panel a user should fall, and hence which implementation we should use for the recommendations. As you can imagine, this is very helpful for running experiments and things like measurable A/B tests, and can provide a very interesting way of testing in a live environment any research or experimentation artifact. In this implementation, every time that we serve a recommendation, we use a hash of the user ID suffixed with a salt to determine to which recommender the user should be exposed. It is very important that this same hash can be calculated in an offline analysis environment so that it is possible to attribute the different results obtained to each of the different recommenders used. We strongly recommend that you append a salt to the user ID so that you are not always exposing the exact same audience to the experiments, but instead you are rotating the audience. Apart from this, we also included a very dummy implementation of the recommender, which receives a static mapping from user to recommendations and always serves those. We use all these implementations in our serving driver, as we are setting up an experiment that will use previously trained ALS model to serve recommendations to the first half of our audience, and we'll use a static recommender to just blindly recommend the other half of our users to drop anything that they are doing and just go watch the Spark Summit, because we think that everyone will enjoy it. Of course, we want to validate the performance of each of the implementations of the recommender in the wild, so we will be performing this A/B test instead of picking one of the recommenders over the other. We will then print the recommendations in the console. As you can imagine, of course, our serving layer can be extended and decorated to include ideas as crazy as we can think. Okay, so now that we have seen how we implemented each of the different decoupled components, let's see how we can glue all this together and run them in one same program. In this very simple driver, we are running the 3 drivers in sequence, and hence relying on the feeds framework to take care of the components' inputs and outputs. We could as well have a different kind of program that doesn't use the drivers at all, but just mix and matches the underlying classes and implementations to run the system using Spark data frames instead of feeds. In terms of testing, we not only structure our code and classes in a way that makes it simple and to add valuable unit tests, Also, a very convenient corollary of having the ability to run these decoupled components in one single program is that we can write very complete automated integration tests that run all the components and perform assertions on the expected outputs. This integration test only asserts that the supported feeds are all populated, but of course it could be extended to perform as many assertions as we want. The fact that we can programmatically force an environment configuration to be used by the system is also very convenient for setting up these integration tests, so that they are isolated from any previous runs. In this case, we are using the target directory in our project to store the feeds produced by the test, as this directory is supposed to be cleaned after the testing is done. Now I will show you how we can run this test. You will see that the test is describing the data frames in the console because we set up the environment to have the debug mode enabled. Of course, we can also leverage the debugging tool provided by our IDE to put a breakpoint at any point in our code and evaluate any expression that we find useful. As you probably know, this would be impossible to achieve in a notebook or when running Spark in a cluster, even though it is a very common practice among software developers. After we are done with all the debugging, we will continue running the test and you will see that the recommender service used the else recommender for one of our users and the static mappings recommender for the other user. You can also see up there that the testing framework accepts this run as a successful run, which is something that we could easily integrate to our continuous integration pipelines to add a very reliable check for our changes. All right, so we hope that this minor example and minor demo is helpful for you. In any case, by the time of this talk, we have made available the code in our GitHub account. We please ask you to feel free to reach out with any comments or questions that you may have, and we will make sure that we answer them in GitHub.
Thanks, Javier. Through this very simple demo, we hope to have shown that even with a very simple notebook, it does take some effort to take a prototype into a software product. Typically, a notebook reflects the end state of an idea, whereas the corresponding software product is the start of a process that adds on many new features. So we think it does pay out the initial effort in the long run. Creating cohesive modules, reusable artifact eases the maintenance and quality by making it easier to test. Furthermore, these artifacts can now be the starting point of a notebook, thereby making research process more effective. An example of this can be importing the jar into a notebook for using the data loader component or by calling the serving layer, whatever. Uh, Additionally, good software products allow for hooks and configuration knobs that allow researchers to test new ideas in production, inject little models such as A/B tests with much lower risk. This also increases the ROI of the whole process as we only promote to production the research ideas that have proven to be successful in controlled live experiments. We want to thank the Spark and AI Summit organizers for inviting us as speakers and making this such a great event despite of the truly devastating pandemic effect. Thank you so much.